I'm Sarithri Alpha, and I'm about to demonstrate a short video which explains a novel consensus algorithm for energy blockchain applications, which utilizes power line communication. This consensus algorithm has been developed to facilitate blockchain as the service architecture for Smart Grid 2.0 applications. This research is jointly conducted by the University of Rijawatanapuram and the Network Softwarization Lab of University College Dublin. What is Smart Grid 2.0? Smart Grid 2.0 is the architecture which combines various components of a modern power system. This includes renewable energy sources, typically solar photovoltaic installations, which you see on rooftops, microgrids, electric vehicles, virtual power plants, and battery energy storage systems that provide ancillary services for voltage stability and frequency regulation. With the introduction of Smart Grid 2.0, novel concepts like peer-to-peer energy transaction, vehicle-to-grid initiatives, and novel demand-side management initiatives have been introduced to the power systems. The key features of a novel smart grid includes decentralization, security, and scalability. Traditional grids exhibited a top-down hierarchy which extended into a two-way communication network with the integration of information and communication technology. This phase we call Smart Grid 1.0. This was further extended to bidirectional power flow, facilitating seamless energy transmission with the integration of Internet of Things, and the novel grid is now known as Internet of Energy or Smart Grid 2.0. The evolution of smart grids was facilitated through the integration of Internet of Things and next generation communication technologies, especially Internet. And as I mentioned, the key characteristics embodied in the next generation smart grids are decentralization, security, and scalable operation. To further enhance the autonomous operation of Smart Grid 2.0, distributed ledger technologies such as blockchain with the inherent features such as distributed storage, transparency, traceability, tamper-proofness, non-repudiation, pseudonymity has stood as a facilitator of Smart Grid 2.0. However, integrating blockchain with Smart Grid 2.0 architecture has its own challenges which need to be overcome. This includes catering the heterogeneity of application for energy security while maintaining quality and reliability, increasing scalability, reducing the computation burden, and ensuring trust, security, and privacy of the users. Having a quick look at the existing solutions, we have identified that blockchains run in consensus with participating nodes who decide which block, considering the validation transaction, should be added to the sequence. In this aspect, the existing blockchains provide state-of-the-art distributed ledger technology solutions which incorporate consensus algorithms such as proof of work, proof of stake, and practical Byzantine fault tolerance. The major drawbacks identified with these consensus algorithms are energy intensivity, lack of scalability, and the associated additional computation burden. Hence, our objective was to eliminate the additional work performed while reaching consensus among nodes, enabling energy efficiency and focusing on the main process that is energy transaction and monitoring. The high-level block diagram of the proposed solution can be seen as follows. First, if we identify the stakeholders that engage in the process, they are prosumers, who are both sellers and buyers of electricity, consumers, and the distribution system operator. If we look at the miners of the blockchain network, they are the nodes who have signed up, which can be either a consumer, prosumer, or a third-party sensing node, which involved in monitoring power flow. It generates a one-time session key and transmits it through the power line. The hash of the same is encrypted by the session key and shared along a known communication channel, which we suggest as the 5G network. Miners then monitor the power line data through their smart meters and try to capture the key in full to claim the reward of the newly mined block. The miner who captures the key, which can decrypt the shared message, will broadcast a new block adding validated transactions and the captured session key. The remaining miners validate the captured key against the shared key by comparing and computing the hash of the either. A new block is then added to the blockchain. The measurement data gathered while monitoring the smart grid is stored in IPFS for power quality assessment. Next, we move on to the simulation setup, which is used to test the validity of the proposed algorithm. Here we have considered transmitting and receiving nodes and a secret of a specific length of bits. The simulation platform which is used for this particular purpose is the process analysis toolkit. Process analysis toolkit is the widely used technique for the formal verification of a process. Formal verification is used to ensure accuracy and verify the model of the proposed consensus mechanics. And this is done through the path simulator. The path simulator develops the system model using a sublanguage of communicating sequential process, also known as CSP. And this allows modeling of multiple complex processes simultaneously, and program generates a state transition diagram by analyzing all possible changes of state. Further, the path checker allows validating the system against predefined properties, also known as assertions, as well as user-defined conditions. The assertions that we selected for this particular scenario are to check whether the proposed consensus algorithm has the capability of reaching consensus, whether it exhibits a no-fork probability, as well as to check further freeness from deadlocks. As you can see, state transition diagram that is expected for this particular process is shown in the figure. We start the process, a particular node that is selected will generate the key, and the assigned transmitter node will transmit the key, and the rest of the nodes will try to receive the key. The transmission and the recipient of the key will be continued repetitively until one particular node is successful of capturing the key input. If so, and the winner is verified, process will stop and a new session will start, which will repeat the exact same process. Now let's move on to the demonstration of the formal verification simulation. This is the path simulator environment, which allows us to code the process sequence using CSP language. This particular simulation involves 6 nodes, out of which one is the transmitter, while other 5 are considered to be recipient nodes. The proposed algorithm is coded, and the assertions were checked for 4 cases, which include case 1 with no malicious users, case 2 with minority malicious users, case 3 with 50% malicious users, and case 4 with majority malicious users. If we simulate the process, the path simulator will generate all possible states the process could reach, as shown here. Next, we will check each assertion one by one. The path simulator first verifies that the algorithm is capable of reaching consensus in all 4 cases considered, that is, irrespective of the number of malicious users present in the system. Under the verification tool, we select each assertion which we need to verify, and the path simulator will display the result. In this case, you can see the verification result indicates that the considered assertion is valid. Let's repeat the process for all 4 cases. Please note that in this particular simulation, since the total number of nodes is 6, the minority of malicious users is selected as 2, half is selected as 3, and majority of malicious users have been selected as 4. In order to check for the fork probability and the deadlock freeness, we can run the simulation for a sufficiently long time and see if the process is terminated before the time out reaches. However, for the demonstration purpose, I have limited the time out value to 1. Here you can see, after reaching 1 minute, the program has terminated, but a deadlock has not been identified. So I can repeat the same to see if there's a probability of creating a fork, which is an alternative blockchain sequence from the main blockchain sequence. As you can see, the time elapsed is 59 seconds. That is, program has reached the timeout. of the session, and it has not identified a fork probability. So we can repeat the same thing for half, minority, and majority users to see if there's a deadlock occurring, as well as whether there's a fork probability. I've skipped the simulation part of the video, and here you can see I'm running the finite system, and on the bottom pane you can see the time elapsed for the simulation, and as you can see, the simulation reaches the timeout point, and it has not encountered either a deadlock or a fork. So this shows that the proposed algorithm is deadlock free and has a low probability of encountering a fork, as well as it is capable of reaching consensus. So by using the formal verification models, we can ensure the validity of a proposed algorithm, as I have done for my proposed novel consensus algorithm. With that, I conclude my demo video, which discussed a novel consensus algorithm using power line monitoring for Smart Grid 2.0, which has several advantages over the state-of-the-art consensus algorithms that are used for blockchain platforms, which is a dedicated and tailored consensus mechanism for energy blockchains utilizing the main process, that is energy metering of the network. Thereby, we have been able to reduce the energy intensity, improve scalability, as well as get additional advantage of the data that is collected through power line monitoring. And also, we assess the validity of the proposed consensus algorithm through a formal verification model.